Okay, this video is going to be a little bit faster because based on the last video, a lot of this information has already been explained. First of all, you have to understand a circle. A circle, measured in degrees, is measured by this little angle here, 30 degrees. Radians is measured by the arc on the outside of the circle. So as you already know, and you know most of this, radians measures as we go around the circle on the outside. Well, we know a circle has 360 degrees. How much for a unit circle, which has a radius of 1, is the distance around the circle? Well, we know the formula for circumference of the circle is 2 times pi times r. But in this case, we're working with the unit circle just to make things clearer, and r is 1. So we can just ignore r, which means the total distance around a unit circle is 2 pi. The equivalent in degrees is 360 degrees. Just be aware they're measuring different things. This is called an arc. It's the area of the path along the circle, and it measures a distance, essentially. Arcs are far more useful mathematically. All these things are mathematical usefulness. For instance, even though I know it's 30 degrees, I cannot use that 30 anywhere in a math formula. It's why they came up with sine of 30, which is a decimal representation, and it can be used in a math problem. So sine of 30, the 30 can't, but 0.5 can, the sine of 30, and as a result, the sines of and the distances of these radians can be used more accurately than the 30. That's why we're switching. So now we've discovered that 2 pi is the full way around, and by logic, half a pi is, or half the way around, is 1 pi, which means 1 pi is equal to 180 degrees. This is why we use this conversion rate. If you want to find out what radians are in degrees, you multiply it by 180 divided by the pi, so that the pi's cancel out, and you're going to get degrees. If you want to convert degrees to pi radians, you take your degrees and you multiply it by pi divided by 180. So the 180 will end 180 degrees, so the degrees cancel out, and you're going to get some fraction. But it always is measuring what's called the arc. Okay, so that's the first thing. We know that all the way around is 2 pi. So that means if all the way around is 2 pi, we can say, okay, if I go all the way around, I reach here again, it's 2 pi. And if I go halfway, I reach pi. And if I go a quarter way, that must be half of the half, it's pi over 2. And if I go 3/4 of the way, and it always starts here, it always starts at origin, and it always goes counterclockwise. And if I go 3/4 of the way, I reach 3 pi over 2. So now we have our main points, and we started at 0 as well. It comes back to 2 pi. So 0 to here, quadrant 1, is 0 to pi and a half. Quadrant 2 is pi over 2 until pi. Quadrant 3 is pi all the way to 3 pi over half, and quadrant 4 is 3 pi over 2 all the way to 2 pi. And this will help us determine our cast rule. So wherever these angles fall in, and they're essentially angles, I'll refer to them as angles, whichever quadrant they fall in determines the cast rule. That's important. It will also determine the acute angle. So let's talk about the acute angle again. If I start with my unit circle and I draw a Cartesian graph right through the middle of it, whoops, try again, right there, I also get some xy coordinates as I go around. And that's important too later on. I won't draw them all, I'll just start there. But a principal angle, this is the terminal arm when I draw any line to the edge of the circle. That red line is the terminal arm. What's the principal angle? Okay, well, since we always start at origin, essentially, at 1, 0 and go around, the principal angle, let's say I stop there, the principal angle is always the angle all the way back to the beginning. That is the principal angle, always. What's the acute angle? The acute angle, as the name implies, is an angle that's less than 90 degrees, smaller than 90 degrees, And in this case, the easiest way to get to it is always going to be, we always want to focus on the x-axis. Why? Because we can always draw a right-angled triangle there and use our knowledge of SOHCAHTOA to figure everything out. So that means the acute angle that we're talking about is here, and the principal angle is in red. Also keep in mind that when we measure in radians, we're measuring the distance that we travel along here and reach there. And when we're talking in the acute angle, we're measuring the arc. And when we're talking in radians, we're measuring the arc, which is the distance here, right there. Why do we like to work in acute angles? Because if you can figure out the first 90 degrees, you can figure out the rest of the triangle. Now, that takes a longer video to explain that. But let's start again. Let's look at a principal arm that falls. Let's make it red. Let's look at a principal arm that falls in the first 90 degrees, just to understand things better. It turns out that a principal arm that falls in the first 90 degrees has a terminal arm that falls in the first 90 degrees has a principal angle that is the exact same as the acute angle. So in Quadrant 1, we discovered that the principal angle and the acute angle are the same. Once the terminal arm travels past 90, that is no longer true. So in this case, the terminal angle, the principal angle, is this. And if I call it terminal angle, just realize I mean the principal angle. But the acute angle is always the distance to the x-axis, always the less than 90 degrees, is that. And why can we find that they're the same thing? Well, if you look at this spot right here, this will always have an x and y value. Well, it turns out that if I draw a right angle triangle for the acute angle, this is the y, how much we go up there, and this is the x. But it also happens to share the same x and y values as the principal angle, because we're going to end up at the same spot as when I draw this blue triangle. So that means if I can figure out the SOHCAHTOA of this blue angle, I essentially will know the sine and cosine and tangent of this red angle. And that's why it's always easier to learn, because it's easier to work with the first 90 degrees than it is to work with, trying to figure out this triangle here. Right angle triangles, as you've already realized from sine and cosine law, are much easier to figure out their distances using Pythagoras' theorem. So that's why we always try to focus on the acute angle. But look, let's ask with this question. For each of the trigonometric ratios, so these are all going to be principal angles, determine in which quadrant they fall. So quadrant 1, 2, 3, 4, and the cast is C, A, S, T. Tells you which trigonometric identity is positive or negative, and the others will be negative. Which quadrant does the terminal all form on, where the principal angle lies, so it's always going to be that red angle, and the value of the related acute angle, so we need to find this blue angle, and the sine is going to be based on cast. All right, that's fair enough. We just need to figure out all these angles. Let's start with this one. How do we figure out where this falls? We can either convert it to the degrees, or we can know our knowledge that we figured out before in terms of 90 degrees. We determined already was pi over 2. And we already determined that 180 degrees is pi. And we already determined that 270 degrees is 3 pi over 2. And we already determined that once all the way around is the same as 2 pi. Now, if you look at these as fractions, this fraction up here is a half. This fraction over here is 1. This fraction over here is 3 over 2. This fraction over here is 2 over 1. And we just have to figure out where this fraction fits within those fractions. So we ask ourselves, is 3/4 more than a half or less than a half? If it was less than a half, it would fall in quadrant 1. And this goes from 0 to a half. 3/4 is clearly more than a half. So then we have to ask, is it more than 1 or less than 1? 3/4 is clearly less than 1, but more than a half, which means it falls in this quadrant. Great. So we're going to draw that. Let's draw it. We're going to draw the principal terminal arm in this quadrant. Doesn't matter where we put it. We just take a guess. And therefore, we know that the principal angle, which is always this, is the same in radians as this. And it would be the measurement of the distance all the way around this arc. That's what this is. It's a distance around the arc. But we'll just think of it in terms of an angle. The question becomes, what is this angle right here? What is this angle? Even though I know I'm talking about the arc, I'm going to call it an angle. Well, we know that if we would go all the way around, we would reach pi. But we didn't go all the way around. We went to here. To figure out what angle is left there, we would take pi and we would subtract all this to figure out the remaining angle. That's logical, isn't it? 90 degrees minus whatever this angle is will give me this angle. Sorry, 180. And pi, since it's the same as 180, minus this fraction, so this fraction minus this fraction, will tell me the blue angle fraction. Okay, so according to me, in quadrant 2, we're always going to use 1 pi minus 3/4 pi. Well, we can't subtract two fractions like this. I have to put this over 4. So I multiply the top by 4 and the bottom by 4. So I get 4 pi over 4, which is 1 pi, minus 3/4 pi, and I get 1/4 pi. So that means 1/4 pi is the same as pi over 4. That means this little blue angle right here is pi over 4. It just so happens I can steal this right there. Steal a better version of it. Like that, and I'll just do that and get rid of the 3. So now I know my acute angle. However, I do not know its sign, because the acute angle is essentially always going to be, in quadrant 1, it's always going to be positive. So remember that. Acute angles are always positive. And that's because they're always less than 90. And when we take angles less than 90, it's in the A area of cast. It's always positive. This one here is not necessarily positive. It depends if it's a sine, a cosine, or a tangent. And by my rules of cast, CAS, S is here is the only thing that is going to be positive. Well, what are we looking at? We're looking at sine. Okay, that's good. That means my sine value of my principal angle is going to be positive, and all acute angles are positive. So that means I can immediately say sine of 3/4 is equal to sine of pi over 4. They're going to have the same sine value. And actually, I forgot to put the word sine in there. But they're going to have the same values because they're both positive. I don't have to put a negative in front, -1 in front of either one of them to make them equivalent. So I've just found an equivalent angle. Let's make sure, though, I'm answering all the questions. Okay, use a sketch to determine which quadrant. Just did it. Terminal arm, drew it. Principal angle, drew it. The value of the acute angle, we figured it out. And the sine, well, we know it's positive because we're in the acute, or when they say the value of the sine of the ratio, they're talking about this ratio because acute angles are always positive, so they don't need the acute angle. They want to know the sine of these ratios. And we already determined, because we're dealing with sine, and it falls in quadrant 2, that sines are positive. Cast. Sines are always positive. So memorize cast. Great, let's move on. Let's we'll go straight to here and we'll just use this again. We'll do a clean one. All right, let's go to the next one. Just make it a bit bigger. Where does this angle fall? Do the same process. Draw your, since they want us to sketch it, we might as well sketch it. We know that pi over 2 is up here. We know that pi is over here at 180 degrees. We know that 3 pi over 2 is over here. And we know that 2 pi is a full circle. Let's figure out where 3 over 5 exists. Well, let's focus on the fraction. 5 over 3. 5 over 3 is definitely more than 1. It's 1 2/3. So since we know it's more than 1 pi, we know it's past this point. The question is, it's past this point. Is 5/3 more than 3/2? Now, one way to do this is put them over the same fraction. So the same fraction for these would be multiplying this by 2 over 2 and multiplying this by 3 over 3. I'd get 9 over 6, and just seeing if the fractions are bigger. So I multiply this by 2 over 2, and I get 10 over 6. Is 10 over 6 bigger than 9 over 6? Yes, it is. So I know that it's in this fraction. I also know it's 1 2/3 is less than 2 pi, so I immediately know it falls in this area. What's another way to know if it falls in this area? Well, I can go 1 pi, and since I've gone 1, I can get rid of it. I just need to figure out 2/3 pi. Well, I know that 90 degrees is half a pi, so the distance from here to here is half a pi, and I know that 2/3 is bigger than half a pi, so again, I would know it would fall in here. Okay, let's go back and draw it now that I've confirmed where it falls twice. I take my terminal arm. It's as if it's in a unit circle. It goes to here, it's one distance. I go all the way around, there's 1 pi, there's 3 half pi's, and I fall somewhere here. And then I draw my principal angle. My principal angle always starts at origin and goes this direction always. For positive angles, negative angles go the other direction. Positive angles, which is generally how we will always think, go this way. And I'll discuss coterminal angles in a second. By the way, a circle, as you know, you could spin in circles forever, right? And just as we only deal in the first 90 to figure out all the other quadrants, we only deal in one full circle to figure out other circles. But a circle, I can go around once, twice, 3 times, 4 times. And you've probably heard terms in skating and snowboarding. He did a 720. Well, 720 is going around once, 360, and around twice to 720. 720 is coterminal to 360. Means I'll end up at the same spot. I'll end up at here. If I go around a circle once, I end up here. If I go around twice, I end up at the same spot. It's coterminal. If I go another 360, I end up at the same spot. So I discover if I add 2 pi or 360 to any angle, I end up at the same spot. So that's important to realize. But let's just focus on our drawing. I'm done. I got my first drawing down. This angle, this coterminal angle, this principal angle, not coterminal, is 5 pi over 3. But the question always remains, what is the acute angle? And the acute angle is always the shortest angle here. Well, for quadrant 4, as this is, it's always going to be 2 pi minus the angle. That's because if I look and go around full, 2 pi, and if I go back to there. I go back to there. So that means this little blue area is going to be always 2 pi minus the red area to produce the blue area. Okay, let's look at that. So just that's an easy formula to remember. If you end up in quadrant 2, it's always going to be pi minus your angle. If you end up in quadrant 4, it's always going to be 2 pi minus the angle you're looking at. And guess what? In this one, it's unique. It's pi plus the angle. That's because once we pass here, anything extra is past pi, so it's pi plus the acute angle will be equal to the full angle. So this is to find the acute angle, this is to find the acute angle, and this is to find the acute angle. Plus pi plus the acute angle will equal the full angle. Pi minus the angle in question will be equal to the, actually I should say pi minus the acute in this one. Pi plus the acute will be equal to the full angle, the principal. 2 pi minus the principal angle will be equal to the acute angle. Pi minus the principal angle will be equal to the acute, but pi plus the acute will be equal to principal. Therefore, the acute is equal to the principal minus pi. Principal minus pi. So let's put it, since all the other ones are in terms of the principal angle, let's put it in that terms. It's going to be the principal minus pi to figure this one out. It's going to be the pi minus the principal angle, and it's going to be 2 pi minus the principal angle to figure out the acute angles. There's the formulas for all acute angles, and in quadrant 1, the principal angle is the acute angle. They're the same angle. Okay, so you don't need a formula for quadrant 1. let's look at this then. 2 pi minus the principal angle. Here's the principal angle. We're going to do 2 pi minus that. Well, 2 pi over 1, I need to put it over 3. This is over 1. So I have to multiply top and bottom by 3. When you multiply something by 1, which is 3 over 3 is the same as 1, you're not actually changing it. You're just changing how you express it into a different fraction. So if I multiply top and bottom by 3, I get 6 pi over 3, which makes sense because 6 divided by 3 is 2. So what's 6 over 3 minus 5 over 3? It's 1 pi over 3, or simply pi over 3, which means the acute angle is pi over 3. So I'm going to steal this portion, and I discover that the acute angle in blue is going to be that. So that means the principal angle is 5 pi over 3, and the acute angle is pi over 3. And this is the one that we will be focusing on. The next question is, what's the sign of the ratio? Well, we have to look at what we're looking at. We're looking at cosine. So if we take cast, C-A-S-T, the sign of cosine here will be positive, which means the sign when we put this into a calculator will come out positive. Let's continue. And they all do this method. They all do this method. So we're going to do the same thing. We might as well just draw our thing again, and we'll just stop putting the reference points on it and see how we do, just for memory. Tangent. We're dealing with a tangent. The important thing is we're dealing with 4 pi over 3. Where is that? Well, 4 over 3 is definitely 1 1/3. So that means I'm past 1 pi. 3 pi over 2, 4 pi over 3. How do I figure out if this is bigger than that? Well, I can make them the same fraction by cross-multiplying. So I can multiply this by 2 over 2, and I get 8 over 6. And then multiply this by 3 over 3, and I get 9 over 6. Which one's bigger? 8 over 6 or 9 over 6? 9 over 6 is. Therefore, it falls more than 1, but less than that. It falls in this area. Okay? What's another way to look at it? Well, I'm more than 1. It's 1 1/3. So the question is, will 1/3 get past this next part? Here's 1. Will the next 1/3 get past the 270? Well, I know that this distance here is half a pi, and 1/3 is less than a half. So again, I know it will fall into this quadrant. So that's another way to look at it. Which means that 4/3 pi, if I draw my terminal arm, will fall in here. And if I draw my principal angle, it's this red angle, which means that 4/3 pi is the principal angle. So I'll draw it and put a red box around it. The question is, what is the acute angle, which is always drawn between less than 90 degrees, closest angle to the x-axis? So the question becomes, what is this angle here? Well, to do that, I notice that this full principal angle goes all the way around, and this acute angle is just this little extra here. Since I know that to get to pi is to here, the blue angle must be this principal angle minus pi to get that. So again, the blue angle must be the principal angle minus pi. So to subtract 4/3 by 1, I have to put 1 over 3. So that's 3 over 3. 4/3 minus 3/3 is 1/3, which means my principal angle is my acute angle is pi over 3. So I'm going to just steal this. I'm going to get rid of the red, and I'm going to get rid of the 4. And that means my little acute angle is pi over 3. So I'll put a little blue square around it. That's my acute angle. And why do we figure out acute angles? Because once we figure out the first 90 degrees, we can figure out any sine or cosine of these angles. And the first 90 degrees with those exact value triangles, we automatically know 0, 30, 45, and 60 in exact values, which means I can figure out the exact values if they are 30, 45, or 60. And there's more ways to do it later on. So now I figured out the acute angle. I just got to figure out, is tan positive? Is my result going to be positive or negative for this? Well, C, A, S, T. This falls in the T area, so my result for this will be positive. So I can say actually that the tan of this will be the exact same as the tan of pi over 3. Let's use our calculators and verify that. Well, switch to radians. Well, 4 times pi divided by 3. If I take the tan result, first of all, I should get a positive result. I do, 1.732. Now let's take pi and divide it by 3, which is my acute angle, and see if I get the same tan. 1.732. I get the same one. So you can always verify that you got the right answer by plugging them into the calculator and seeing if they do the same. By the way, what is 4 pi over 3 in terms of degrees? Well, we multiply it by 180 over pi. The pi's cancel out. 3 goes into 180, 60. 4 times 60 is 240. So that means the principal angle is 240. What is the acute angle? It's 240 minus 180. So this angle here is 60. So I can even come up with exact values from my exact value chart instead of using my calculator, because I have an exact value for 60 from my previous exercise. Go around and they all follow this rule, except maybe this last one, because you might get confused by cotangent. But cotangent will follow the same rules as tangent, and secant will follow the same rules as cosine. That's because secant is equal to 1 over cosine, and cotangent is equal to 1 over tangent. So that means if tangent's negative, cotangents will be negative. If tangent's positive, cotangent will be positive. If cosine is positive, secant will be positive. If cosine is negative, secant will be negative. They will follow the same rules. Well, let's do the cotangent, right? Because that tends to confuse people more. It's the same process, though. Let's figure out where this 7/4 lies. Step 1. So here are your steps. Step 1. Figure out where that fraction falls, knowing that 90 is equal to pi over 2, 180 is equal to pi, 270 is equal to 3 over 2 pi's, and 360 is equal to 2 pi's, and you can just focus on the fractions in front. Okay, so 7/4 is definitely more than 1. It's 1 3/4. So that means on the unit circle, I've gone past pi, 1 pi. The question is, does 3/4 go past 270 into this quadrant, or does it stay in this quadrant? Well, we can focus on the 3/4. We know the distance between any axis point is pi over 2. So the question is, or 1/2. So the question is 3/4 more than 1/2? Yes, it is. So it falls in this quadrant. What's another way to figure it out? Well, we could convert it to degrees, or we could just ask ourselves, since 270 is 3 pi over 2, we can ask ourselves, is 3 over 2 bigger or smaller than 3 over 4, the angle we're interested in? We multiply this by 2 over 2, and we get 6 over 4. Oh, hang on, does that work? Yeah. And then we have to look at the 7 over 4. So is 7 over 4 bigger than 6 over 4? Yes, it is. Therefore, it falls in this angle. So 6 over 4 represents 3 over 2, and 7 over 4 is the angle we're looking for. So that's another way to realize it falls in this quadrant. So let me draw it with a terminal arm. So the terminal arm starts here and goes woo right to there. And now I'm going to draw the principal angle. It always does that. So of course the acute angle that we're looking for is actually right here. That's the, oh, sorry, it's not. My bad. Always to the x-axis. I don't know why I fell asleep to switch there, but I did. That's always going to be the acute angle. How do we figure it out? Well, we know in this quadrant it's all the way from 360. So to figure out that blue angle, it's 360 minus the principal angle, or 2 pi minus the principal angle, which is 7/4 pi. In order to subtract this, I have to put this over 4. I have to multiply it by 4, top and bottom, and I get 8/4 minus 7/4. I get 1/4 pi, or pi over 4. That means that acute angle is pi over 4. So I'm just going to steal this angle like this, make it a bit smaller, and put it right there, and put a little red box around it, blue box rather. So the acute angle is pi over 4, and my principal angle in red should be is 7 pi over 4. So I should also put it over here, and actually I'll just steal the red box, put it right over there. So that's the principal and the acute. So the only question is, are we dealing with positive or negative? So cotangent's the same as tangent. It goes C-A-S-T. So tangent in this area, since it's not cosine, it's negative. So the sign of the ratio will be negative. Sure enough, if I take 7 pi, 7 times pi, and switch to radians, and divide it by 4, I get this. And if I take the tangent of it, I get a negative result. By the way, pi over 4 is 45 degrees. And for 45 degrees, it's the only time cos and sine are the same angle. And since tangent is equal to sine divided by cos, and they have the same cos and sine values, it will always be a tangent of 1 or negative 1, depending which quadrant you're in, for 45 degrees. So tan of 45 is always a version of either plus or minus 1. And that's because cos is equal to sine 45 degrees in terms of value. And when you divide one by the other, you get 1. Anything divided by itself is 1. Okay, so that's how to do that. That's pretty much all you need to know. The only other question I know, as you said, is a little confusion about coterminal angles. Well, once you figure out your angle, let's say we're dealing with the same principal angle of 7 pi over 4, or 3, I think it was, 4. We can figure out any coterminal angle by adding 2 pi to it, or 4 pi, or 6 pi. And that's because this represents one full circle. And if I go from this spot, and I go 360 degrees around, I end up at the same spot. Since 2 pi is 360, I can add or even subtract a version of 360 to this fraction and end up at a coterminal angle. Same with the angles. If I add 360 to 270, what's 360 plus 270? It's 630. That means 270 is coterminal to 630. They are the same angle. They will have the same sine and cosine and tangent results. Let's see if that's true. Let's take the sine of 270. Try to remember, it's negative 1. Let's take the sine of 630. Negative 1. No matter what you do, if you add or subtract 360 or any multiple of 360, you will get to a terminal angle that has all the same sine, tangent, and cosine values. And that's why we learn the first 90 degrees to learn the other quadrants. And that's why when you learn the full circle, you know any angle on the planet. It's also why a sine curve, why this represents the sine values of one full circle, and then as you repeat it, it repeats every 360 degrees. So this first area is 360 degrees. This next area, right here roughly, is 360 to 270 degrees, 720 degrees. This next area, roughly, is 720 to 1080, and so on, every 360 degrees. That means the period repeats over and over and over again. Once you figure out the first 360 degrees, you can simply add one period, because sometimes these periods change. But if you're working with the parent function, you can simply add 360 each time, to figure out where it repeats. Or subtract 360 because the sine curve also goes this way. And that's because you can go around, you can just like a skater, you can go around once, twice, 3 times, 4 times, 5 times, and as long as it's 360, you end up at the same spot. You can also go the other direction, right? So this would be negative angle, would be this way. Once, twice, 3 times, 4 times, I end up at the same spot. Those are all coterminal angles. Pretty easy actually to figure out coterminal angles.